Good day students. In this session we will be discussing about ideal solutions and non-ideal solutions. Ideal solutions are those solutions which obey Raoult's law under entire range of concentration. Also, there are three conditions which should be satisfied in order that we can say that that is an ideal solution. The properties of the ideal solution. The first and the foremost property of the ideal solution is that delta H mix should be 0, which means that there should not be any change in enthalpy when both the components of the solution are mixed. That is, their heat should not be evolved or absorbed when both the components of the solution are mixed. The second condition is that delta V mix equal to 0. That means that upon mixing of the two components, there should not be any change in the volume of the solution. And the third condition is that the intermolecular attractive forces between AA and BB should be nearly equal to those between A and B. Suppose we name one solvent as A, another solvent as B. Then ideally speaking, there are three types of, if we see at molecular level, there are three types of intermolecular attractive forces operating in the solution. The first type of intermolecular attractive force is between the AA type or between say solute-solute type. Second type of intermolecular attractive force is between the solvent-solvent, that is BB type. And the third type is between the solute and the solvent, that is the AB type. If the solution is ideal, then the intermolecular attractive forces between AA and BB should be nearly equal to the attractive forces between A and B. But all the solutions are not ideal solutions. Ideal solutions are very rare. For example, we have few examples of ideal solution like N-hexane and N-heptane. They form ideal solution. Also bromoethane and chloroethane also form an ideal solution. So if the solution satisfies these three conditions, then it can be named as an ideal solution. Next is non-ideal solution. The solution that does not obey Raoult's law under entire range of concentration is known as non-ideal solution. In such solution, what happens that the vapor pressure of the solution is either high or either low than the expected value from the Raoult's law. Why does this happen? The reason being that if the experimental vapor pressure is higher than the expected value, then it is known as positive deviation, and if the experimental vapor pressure is less than the predicted value by Raoult's law, then it is known as negative deviation. Now, what is the reason for this positive and negative deviation? As I have told you earlier that there are three types of intermolecular forces of attraction operating. In positive deviation, what happens that the AB molecular interactions are weaker than the AA and BB type of interactions. Meaning to say that the solute-solvent molecular interactions are weaker than the solute-solute and the solvent-solvent interactions. So what happens that the number of the solute and solvent particles escaping into pure state, it is greater, and hence it is greater, and hence there is an increase in the vapor pressure. So if we see graphically, if we plot the graph of vapor pressure versus the mole fraction, then according to Raoult's law, this blue dotted line shows the graph of P. This is the graph of PB naught. This is the graph of P. This is the graph of PB. This is PA and this is PT. Total pressure that is equal to PA plus PB. This is according to the Raoult's law. But for non-ideal solution, in case of positive deviation, we saw that the solute-solvent interaction is weaker, and therefore the number of solute and solvent particles escaping into pure state is more, and hence the vapor pressure is more. So we find that according in non-ideal solution, the experimental value of vapor pressure is shown by this green line. This is the experimental value of the vapor pressure for B, This is for A, and this is PT, which is greater than PB plus PA. So here PA is greater than PA naught into XA. PB is greater than PB naught into XB, and therefore PT, that is total pressure, is greater than PA plus PB. This is the example of a positive deviation from Raoult's law, in which the experimental value of the vapor pressure is greater than as predicted by the Raoult's law. Next is negative deviation from Raoult's law. In this case, the solute and the solvent interactions, molecular interactions, are stronger than the solute-solute and the solvent-solvent interactions. Hence, the number of solute and solvent molecules escaping into the pure state decreases, and hence their vapor pressure also decreases, resulting into the negative deviation from Raoult's law. If we see the plot of vapor pressure versus mole fraction, here the dotted line shows the graph of partial pressure. This is a vapor pressure PB, this is for PA, and this is for PT, that is equal to PA plus PB. This is according to the Raoult's law for ideal solution. But if the solution is non-ideal and if it has a negative deviation, then this blue line shows the experimental value of the vapor pressure. This is PB, which is less than PB naught into XB, and this blue line, it is PA, which is less than PA naught into XA here. So PA is less than PA naught into XA, PB is less than PB naught into XB, and total pressure PT is less than PA plus PB. The examples, the solutions which form negative deviation, which show negative deviation from Raoult's law, are chloroform and acetone, and another is phenol and aniline. So here in negative deviation, the experimental value of the vapor pressure of the solution is less than that as predicted by the Raoult's law. While here in positive deviation, the experimental value of the vapor pressure is greater than that as predicted by the Raoult's law. And the next topic of our this session is azeotropes. Azeotropes are binary mixture of liquids having same composition in the liquid phase as well as in the vapor phase, and they boil at a constant temperature like a pure liquid. And the components of the azeotropes cannot be separated by a fractional distillation. They just behave like a pure liquid, and hence their components cannot be separated by fractional distillation. Okay. There are two types of azeotropes, maximum boiling azeotropes and minimum boiling azeotropes. Now, minimum boiling azeotropes, the solutions which show large positive deviations from the Raoult's law, they form minimum boiling azeotropes. Example is ethanol and water. While the solutions which show large negative deviation from Raoult's law, they form maximum boiling azeotropes. And for example, nitric acid and water. So we can say that azeotropes are binary mixtures of liquid having the same composition in the liquid phase and the vapor phase, and they boil at constant temperature and they behave like pure liquid. That's all for this session. Thank you.